Hello, everybody. My name is Jack Jablonski, and I am a member of the AI Success team working out of our Chicago office. In today's learning session, we're going to talk about explanation insights with clustering. Today's presenters are Rajiv Shah. He is a data scientist at DataRobot, where his primary focus is helping customers improve their ability to make and implement predictions. Previously, Rajiv has been part of data science teams at Caterpillar and State Farm. He has worked on a variety of projects from a wide-ranging set of areas, including supply chain, sensor data, actuarial ratings, and security projects. He has a PhD from the University of Illinois at Urbana-Champaign. We also have Andrew Mathis. He is a customer-facing data scientist working with DataRobot's public sector practice, supporting federal agencies in building up AI capabilities. Leveraging his background in social sciences, statistics, software development, and consulting, he is developing use cases, advancing federal missions, and creating efficiency in government operations. And lastly, we have Chandler McCann. He is the general manager and chief data scientist at DataRobot's public sector practice. Previously, Chandler led engineering and analytics teams in semiconductor manufacturing at Micron and data science teams at the Pentagon. At DataRobot, he has supported enterprise clients on a range of projects, including anti-money laundering, demand forecasting, media, and predictive maintenance. He has a master's from the University of California at Berkeley. Also, we'll have an opportunity for Q&A throughout the session, so please feel free to add your questions to the dialog box during the session, and we'll address them in order. As a reminder, all of these are recorded and available on the community website. And if you have additional questions, you can email us at aisuccess-webinars@datarobot.com. Now I'll hand it over to Rajiv.
All right. Thanks so much, Jack. So this is another one in our kind of continuing technical series where we want to focus on practical kind of data science solutions for you. Today, we're going to focus on explanation clustering. So when I joined DataRobot about 3 years ago, one of the great things about DataRobot is it gives you explanations. And I quickly started playing around with it, and over time have played around with it, but also lots of other folks within DataRobot introduced me to the concepts. Today we have Chandler that's going to be working with us, and Chandler and I worked on this for quite a while. One of the other people I want to mention is Taylor Larkin, who was also working with Chandler and I, spending a lot of time huddled over computers, figuring out kind of the best methodology here. Today, we also have Andrew sharing some of his experience and some of the code that he's actually put together, the R package that's listed there. We have another member of our team put together the Python notebook that you can see that's listed there as well. And so we've had lots of other of our data scientists from around DataRobot contribute to this clustering and working with their customers on it. So I'm excited to kind of share this with you, but just wanted to highlight that there's a lot of us that have been working around this. The flow, what we're going to do today is just start with a background on what are explanations, why we care about explanation clustering. Then we'll walk through the methodology. We'll also have Andrew walk through kind of the quick vignette of the R package so you have an idea of how that would work. And then we'll kind of end with some of the successes, some of the different examples our fellow data scientists have shared, how customers have used this as well. Now, throughout the session, as Jack mentioned, go ahead and fire questions as well. I'll try to kind of stop every once in a while and make sure we answer them. All right, let's get going. Okay. Do I sound okay to everybody else out there? Can somebody double check? I saw there's one comment about that.
Yeah, you sound pretty good. You're good.
Okay. So as a starting point is what we're going to focus on here are explanations. And for those that are unfamiliar with it, let me just hit this very quickly. What explanations are is when you get a prediction from DataRobot, you also have the opportunity to get an explanation, which is an ordered list of the relevant features for that particular row or prediction. So in this example here, we can see for one row of data what the prediction was, 67, but we can also see what are the other factors here that contributed to having this prediction compared to the base value. Now, explanations are terrific when we're working with individuals. A lot of our customers will take this, put these explanations in a dashboard, and provide a lot of context when they're trying to understand what's going on with a particular row of data. But what I want to focus on today here is when we start using those explanations in a bit different ways. So one of the first things people will start doing with these explanations is just, instead of looking at one individual explanation, let's start looking at all of them. So I grabbed this from Nick. This was one of his insurance customers had laid this out. And they basically just took all their explanations that they had for many different customers and plotted them out. The color here refers to the prediction strength of it. And this allowed them to kind of identify patterns in their predictions. And so you can see this is a little bit of a preliminary for what we're going to talk about. I've played around with this and done the same for time series, for example. When we're thinking about selling different products, they all have different types of factors that influence them. So in this case, this is the jewelry. And one of the things you'll find with jewelry is if you're selling it and it's not the holiday season, well, having sales is a strong indicator that's going to lead to higher sales for jewelry. Now, these same explanations wouldn't apply for something like lawn and garden, but it's how we can start taking these explanations and getting new insights. A couple of other examples we've done is folks have taken these explanations that come out, used them to generate personalized messages for marketing, and then segmenting customers based on those explanations as well. You can take these explanations, and often in a manufacturing context, we've done this several times, is look at your explanations over time. And one of the things is what this allows you to do, and as you'll see with the explanation clustering, is explanations you can think of almost as a form of dimensionality reduction, just helping to reduce the space of information to focus on the most crucial information. And so we've been able to use this with manufacturing, for example, to better understand what are the effects of a fault. All right. So let me jump into kind of the meat of it, what I want to talk about today around explanation clustering. Now, we often give predictions at that individual level, and we often tell customers most of the time, that's great. You want those individualized predictions for a specific customer. But often in a business situation, there's often reasons that we want to use clustering. We want to be able to group customers together, sometimes to tell a narrative. If we're running television ads, we might not be able to run a specific individualized television ad for every person. Right? It makes sense to kind of group or lump people together into some type of segmentation and then be able to approach them. So what I want to focus on today is this explanation clustering is a technique that can provide you the clusters for this. And one of the things that often comes up with DataRobot is we get asked this all the time, like, hey, why don't you just add a stinking k-means button to DataRobot? Like, how come you don't have clustering right inside the platform? And so I'll give it my take on this, and maybe Chandler, you can kind of take over after this with your take. But historically, DataRobot has always had a very opinionated way of doing data science. Our focus is often on making sure customers get value. And one of the things we see, and our CEO is a data scientist, right? He comes from this as well, is it's very easy when you start getting into the unsupervised and clustering realm to just spend a lot of time trying different techniques, right? You have the Stack Overflow article on how to figure out what the number of clusters is. And without that clustering in that unsupervised way, since it's not anchored, we see data scientists spending a ton of time on clustering without adding value. Where instead, if what they did was focused on labeled data with groups there, they could quickly get a much faster signal and performance. And one of the things that happens with clustering, so for example, had a huge group of customers and we're trying to segment out our customers. Traditionally, we have lots of different types of data. We might have very high cardinality data. We might have text data, image data, location data. all of this stuff is going to, for one, it's going to just increase dimensionality, right? Which makes it a little bit harder to use some of our clustering methods with very high dimensions. But we also know that a lot of the features might not really have any bearing, right? As a data scientist, the first thing I do is I suck up and grab all the data I can, but some of that data might not really have anything to do with if somebody's purchasing. But if I just naively apply some clustering to it, it's going to treat all those features the same. So this is, as we'll get into, kind of one of some of the advantages of explanation clustering. All right, Chandler, you want to jump in now?
Yeah, thanks, Rajiv. Can you guys hear me okay?
Yeah.
Fantastic. Yes, so as Rajiv mentioned, clustering explanations really neatly addresses some thorny issues that exist with typical unsupervised clustering. And it's a salient point for me as well when we think about starting with our target first and what we're trying to predict, as opposed to starting with what's just sort of related and near each other. I think it tells a better story around what's happening with our data. And I think, and we'll walk through this in detail, the story you can end up with explanation clustering, it's just a little bit more crisp around what's driving sort of areas of your lift chart. So what do I mean? When we talk about explanation clustering, like what's really going on? At the simplest level, we're just clustering groups of predictions that have similar explanations. And the intuition is that while the explanations themselves really help us at the record level, clustering them helps identify groups of features or patterns that summarize entire probability groups, right? So importantly, we also base it off of information that's the most predictive for that group, and like Rajiv mentioned, not just correlated or related to other features nearby. So what you end up with is a way to summarize different segments of our lift chart using the cluster centers as representatives. Now, as Rajiv mentioned, this technique was really born out of many efforts in parallel, but one of which was simply noticing that these patterns often emerge when we looked at the explanations for an entire scoring data set. And he showed that before with Nick's example. And we thought clustering was just an effective way to summarize those patterns. And it is easy to overlook, but Rajiv did mention this earlier, traditional distance metrics that are common in most clustering techniques have a very hard time with high dimensional things like text or even high cardinality categoricals. And as text becomes more ubiquitous in our data sets and we become, it's a lot more tractable to handle those in our machine learning models, ignoring that information is really detrimental when you're trying to think about patterns of behavior, particularly when people are giving things like their opinions in response surveys. So this is a nice way of trying to get after that, and the prediction explanations sidestep some of the problems with that that we'll see here in a second. So next slide. So for the next few slides, we're going to talk about how we can implement this at home with DataRobot, and let's just start here. So where do we begin, right? First, we need to have a solid use case and a finished predictive model. And from there, we're going to follow a few simple steps. We want to extract the explanations from the data set. We're going to then pre-process those explanations and use the clustering algorithm to create groups. And then finally, we're going to join those cluster IDs back to get the characteristics of each cluster and help tell a new story there. So let's go ahead and dive in to our next slide. So first thing we want to do is flatten the explanations. And what you're looking at on the left is a representation of what explanations look like when they come out of DataRobot. So here on the left-hand picture, we see that each predicted row is represented and it returns its probability. In this case, it's class probability for a binary classification problem. And then it also is going to return the 1 to 10 most predictive features for that prediction itself. So what drove that prediction up or down? And also its qualitative and quantitative strengths. So we see those 3 plus signs mean that feature small business loan on the top drove the predictions up. But there's actually a number underneath that, and we can use that as a distance measure. But in order to use this for clustering, we need to reshape the data set to a matrix where each row is still that prediction, but each columns are our most predictive features. So we can see that on the right, where we've transformed the column headers to be the features that were present as in the explanation group, so to speak. So then what we're left with is each cell becomes the strength of that feature for that one prediction. So ultimately, we have this matrix of explanation strengths per prediction by features. And DataRobot's going to use the top 50 features in a data set, if there are that many, to create the explanations. So we can be left with a matrix of 50 columns by n predicted rows. Now, you may notice, if you look on the right, that you can see this could introduce some sparsity if a feature wasn't relevant for a given record, but that's something we're going to address down the road in the next step.
Sounds good. And you know, with the new SHAP, Chandler, we're gonna be able to blow it out even wider. So
that's true. That's true. It's a good point. And yeah, so what do we do when this gets wider, right? The next step is to prepare that data for clustering. Now, it's worth noting, and Rajiv can jump in here too, that you can really deviate and chart your own path here. As he mentioned, we've tried a number of different pre-processing steps here, and we found that uniform manifold approximation and projection, which is a mouthful, let's call it UMAP. It's really useful, but you could certainly use other techniques like TSNE or PCA. However, since we're going to leverage HDB scan for our clustering algorithm, which is a density-based approach, we found that UMAP works really well together. The reason being that reducing dimensionality is going to make the density more apparent, and it's going to make it easier for HDB scan to cluster. So UMAP has this really nice property of being nonlinear and manifold aware. So you can reduce that dimensionality down to something small enough that HDB scan could be effective with. So if you look on our right, we've taken our data set and reduced it down to 2 dimensions, which has this really nice property of allowing you to visualize the clusters. But this isn't always the best thing for all data sets. It's certainly useful for telling a story, but I would encourage you to experiment with different settings on your own. And you could evaluate cluster performance with different metrics that are out there, like ARI or AMI. But at the end of the day, we're going to take that flattened explanation matrix and reduce it down to a few dimensions here.
Yeah, and I just echo. Mm-hmm. Yeah, and I just want to echo kind of what you said. Is like a lot of this is just very pragmatic. We've just played around with it. You could just simply use k-means right at the beginning and just kind of be done with it. But we found kind of using this kind of approach works better. And partly the reason I wanted to do this kind of whole piece is because I see some other people in the literature starting to do this. And like, for example, if you look at Scott Lundberg's paper in the SHAP paper, he uses a hierarchical clustering for doing his clustering of explanations. And you can use approaches like that, but I think in our experience, the techniques that we've shown or that we're going through here work a little bit better. Okay.
Yeah, thank you. And it's a great point. You can totally skip the embedding stuff and just jump right into clustering. So at the end of the day, you are data scientists and you have to experiment with a few things. There's never a hard and fast formula. More than one way to bake a cake, as we say.
Exactly. And let us know it works.
Yeah, please do. We'd love to hear. Okay, so if you want to go on to the next slide.
Yeah, you want to go through this one, 3, or are we going right to 4?
Oh, sorry, did I skip this one?
Yep.
Let's go to 3. Yeah, sorry. I guess my screen slowed down. Okay, on 3 with getting the cluster labels. At this point, we've reduced our dimensionality and we've ran our clustering algorithm. And now we simply want to assign our cluster labels back to the data so we can analyze, right? Now, if you look at our data set here, each row is still a prediction, but we have our reduced dimensional values associated with it. But we also have mapped back our cluster labels that it was assigned to. Now, what you may ask is why HDB scan on the right? And as I mentioned before, there's lots of approaches. We've landed on HDB scan, and it's we found that it simply works particularly well with UMAP. Now, the scope of how HDB scan works in full detail is kind of beyond this webinar. But at a high level, it just extends previous density-based approaches and converts it into a hierarchical clustering algorithm, and then uses that technique to extract a flat clustering based on the stability of the clusters. So all that really means is it's going to convert our feature space, our new reduced feature space, into according to density and sparsity in the data, and find clusters that are there. One of the nice features of this is that we don't have to come up with a predefined number of clusters or centroids. They'll find those for us. And it will also identify things that are noise. So what you'll see on the right of this picture here is that it's assigned cluster IDs to things that are colored, purple and red, and things that are gray, it's considered as noise. Now, in this case, this is an extreme example where it's very confident about things that it assigns color to, and not so confident about things that are gray. So it's not going to force something into a cluster unless it meets the criteria that we've set. But one common, if you see something like this is usually because there's still a lot of sparsity in your data, and maybe an indication to reduce your dimensionality a little bit more. But the takeaway is it's not going to force things into clusters unless it meets a certain criteria. So we found this to be a really nice feature, and it's something you can experiment with our package as well. Okay. And I've lost my video here, so I guess we're on slide 4.
Yeah, so it's showing joining clusters to the original data set. Yep.
Apologies about that. Yep, thanks. So this is really where we get to the fun part, right? We're going to merge back in our cluster information into our data of actual values in the original data set. So this is where you can use simple tools like Excel to help you out. So we can map back our cluster information to our original rows of data, and using simple techniques like row level highlights, where we calculate the mean values of each feature per cluster, can help tell a story. So if you look on the right hand side, we've converted where each column is our cluster, and we've taken the average feature values in our data set along our rows, and we can already see patterns jumping out. And this is an example we can touch on later on, but our FAR cluster on the right always has higher values across the board. Our cluster in the middle tends to have lower values, and then we have some ones that are sort of medium with orange right there. So visually, we can start to walk this around desk side to people and see if this makes sense. In this case, this is looking at NBA performance, and our top performers tend to have higher values when it comes to player metrics. So it's passes the intuitive test, but a really simple way to go back to things like we talked about, that high cardinality data, that text data. We can see the impact of those here. Anything else to add on this one, Rajiv?
No, that's good.
Yep. Okay. Now, finally, if we're going on to how we can interpret clusters using DataRobot, we don't have to stop just looking at means. There's a lot of things we can do, and at DataRobot, we love to experiment and take advantage of our automation. So one thing we can do is to simply go through and create a new project where we're trying to predict if a row of data belongs to a cluster or not. So we could create a number of one verse all projects. So let's say I have 5 clusters. I could create a project in DataRobot binary classification where I say, hey, does this row of data belong to cluster 1 or not? And then using some simple tools like feature impact, which is on our right-hand side, I can see which variables are driving my predictions of belonging to a particular cluster or not. So we can also use other tools like partial dependence to look at the how features are important for a given feature. But the idea is you can get creative, and I'm sure there are other tools, and we'd love to learn more about what you all are doing on your own to sort of help tell a story here. But it's a nice way to quickly automate this process and start to understand what's driving these clusters and this kind of patterns of behavior. And I think this will get a little bit more, sink in a little bit more when we talk about our examples down the road. So just some words of caution though, if you do use this approach, it's important to try to use the full sample size when we're looking, we're permuting, particularly with smaller data sets for future importance, because permutation importance does introduce some randomness, of course, to the process. But like all things, you can't just rely on one technique. We encourage you to compare multiple approaches and insights. Okay.
All right. You want to talk through this, or I can? Right. We have a number of different implementations that we've made of kind of our explanation clustering, and this week we put them out on our community GitHub. So if you go out on GitHub and you look at the DataRobot community organization, you'll see a bunch of different repos that have to do with kind of data scientists using it, but we've made two specific repos, one for the R package we have that we're going to demonstrate, and then as well as we have a Python notebook that walks through using explanation clustering itself. We have a bunch of internal resources, but for now, for most of you, those are probably the easiest ones to get to. And I think what we want to do next is have Andrew walk through an example of using the R package with DataRobot. All right. Jack, can you help Andrew take over and share screen?
Yep, you should be able to grab it. Then me. There you go, Andrew.
All right, I'm attempting to show my screen now.
Yeah, you are good.
Perfect. So hello, everybody. Thanks again for joining. So what I'm going to be going through here is illustrating the R package that we've put together to implement the techniques that we've just been discussing. So you have the link to the DataRobot community page where we have a repository implementing this R package. This is what the code looks like, but probably a little more interesting to actually show you, rather than the code, an example going through and see what the results are going to look like. So what I've put together here is a Jupyter notebook, and this is going to echo the documentation vignette that's inside the R package. So if you're interested in running through this yourself, once you install the package, that vignette is going to be available for you to work through yourself in R Markdown. So because it's hosted on the GitHub, it's a full-fledged, properly formatted R package. In terms of installation, we can just use the DevTools install GitHub function to install the package. So in just one line, you can reach out to GitHub, grab the package, and install it just like any other R package. And once it's installed, we can load that up just like any other R package that's installed. And the package name here is this DataRobot PE clustering. So in terms of the example data set we're going to run through today, we're looking at the Pima Indians diabetes data set that's part of the MLbench library. And this is a data set that's looking at diabetes risk among the Pima people, which is a Native American group in Arizona. And so you can see here, each one of our rows is going to be a participant or an observation in our data set, a single person. And we've got a number of measures on various diabetes risk factors. So we have things like glucose levels, blood pressure, mass or weight, a pedigree score, which is just a measure of kind of family background risk factors for diabetes. And then crucially, we have our indicator of whether or not this person has developed diabetes. Now, with prediction explanation clustering, that apart from just the data we're working with, we also need a model that's fit with DataRobot. So I'm not going to go through that here, but I'm just pulling in a model I had previously trained. I just need essentially a project ID and a model ID from my DataRobot interface, and I can pull that model down into my notebook here. So once I have my data and my model, there's really just a single function I have to call from my package to run through that methodology of the dimensionality reduction and the clustering as we were just going through. So this function here, we have to pass in what model we'd like to use to produce those prediction explanations, the data we'd like to run through to produce the prediction explanations on, and then a set of arguments here that are going to inform how the dimensionality reduction is performed, as well as the clustering on the tail end. So I've put in some values here that work on this rather small toy data set, but of course you can explore the optimal values for yourself to see what works best in your particular case. So running this single function here from the package is going to run through that entire process. So it'll take care of calculating the prediction explanations, flattening them, performing that UMAP dimensionality reduction, and then HDB scan on the tail end for the clustering. And what you get back from this method is this results object, which has some summary data, data suitable for plotting, which we'll go through shortly, the actual identification of the clusters as they were returned from the HDB scan, as well as some output from the prediction explanations so that you can continue on and use those in your own pipelines if you wish. So going through here some of the results. So the summary method on the results is just going to give you a picture of how the clusters look on average across your different features in the data set. So this is just a quick summary to get a numerical view of what these clusters are looking like in average for each one of my features. As well, we have a built-in plot method, and that's going to show you how the clusters differ on those reduced dimensions of prediction explanations that came out of the UMAP method. So what you can see here is we got for this data set 3 pretty distinct clusters here shown in the different colors. Now, by default, built into the package, it's just the standard R plotting. But of course, if you are a fan of ggplot, as I am, I make the data available for you in those results to plot with ggplot as well. So this is just the same picture in ggplot. So again, three clusters here. So like we were saying before, just knowing what these clusters are is not the end of the analysis. Now we'd like to bring them back into our data set and start interpreting what they truly mean. So what I'm going to do here is just take those cluster IDs coming out of the output from the method I ran and attach it back to my data set that I had put in so we can do some introspection here. So the first thing I'm going to want to look at is how do the clusters differ by the prediction. So in this case, the predicted diabetes risk. And what we can see from this visualization is we have 2 clusters that have mostly low predicted risks for diabetes, and 1 cluster that tends to have pretty high risk. So we could, as a shorthand, summarize this as maybe 2 low risk groups and 1 high risk group for diabetes. So let's take a look in a little more detail and take a look at what these clusters look like in terms of the source features themselves. So I'm just showing a density plot here for our different clusters across these different features. And some things that leap out at me immediately. We can see here cluster 1 seems to be concentrated in lower ages. So it looks like cluster 1, which was one of our lower risk groups, is predominantly young people. And we can similarly look at our other feature sets to see where these clusters are differing. And I just want to point out here, this is where that advantage of the prediction explanation clustering comes in, rather than just looking at how these clusters, how the observations differ on features in the abstract. We know that these differences are going to be correlated with differences in risk because we're clustering on the prediction explanations. So when I'm seeing differences here, I have a little more confidence that these differences are really meaningful for the problem at hand. So I know that this cluster of young people must have something to do with a changed risk in diabetes. So to get this a little further and to get a little more insight, we can also take a look at these clusters by that flattened prediction explanation strength matrix that we referenced prior. So that's also available in these results. I call it just strength matrix. And we can join the clusters to those as well and visualize here as well. And this is where we get a pretty powerful story coming out. So I mentioned before that we had 2 different low risk groups and 1 rather high risk group. So cluster 3 in blue is our high risk group. And you can see here they have prediction explanation strengths that are high, so contributing to higher risk across glucose, age, mass, looks like also this family history pedigree. So this is where we're getting to flesh out exactly what that high risk group looks like. And in contrast, for our two low risk groups in the red and the green, we can see how they differ in why they are predicted to have low risk. So it looks like, as I mentioned, the cluster 1 is tied to age, and that's a protective factor. We can see that because of the negative prediction explanation strength. And it looks like also they have a negative contribution, a protective contribution from their glucose levels. And we can contrast that with cluster 2, which they're not quite as young, or that's not quite as important in their protective factors, and it's concentrated more over these other factors. So this is just an example output from this toy data set, but the same style of investigations should be valuable for your own data sets and your own problems that you're looking at. And just as a tail end here, I'll mention, I do provide for you in the output the strengths matrix, that flattened matrix of prediction explanation strengths that you could use if you'd like to cluster in your own way or do different styles of dimensionality reduction. You have the output here to work off of. So hopefully you'll find this package useful, and I do welcome your feedback as you start using it. We'd love to hear how you're using it, any troubles you run into, or suggestions for how to make it better. So with that, I'll hand it back to Rajiv.
Yeah, no, really nice job. And this is so much better than the kind of the crappy code I was handing out on this. So I'm, yeah, very excited to kind of have this available for folks. All right. And I think you did a great job, Andrew, going through and explaining kind of, what the value of the prediction clustering was going to be. I have a couple of other examples I want to run through. But if people have questions as well, feel free to kind of just type those in, and we'll start taking those here in a few minutes as well. So a couple of other examples of how our customers have used explanation clustering, just to kind of make it a bit more concrete, how you can start taking advantage of this method. So let's go through, and Chandler, you might chime in on some of these as well.
Yep.
So one of the early ones I had worked on was with one of our Japanese customers, where they were looking at net promoter scores. So this is kind of a very popular way to look at customer satisfaction. And they wanted to see, can you tell us about the folks that are getting low NPS scores, the ones that are actually moving that way? And we were actually able to use the explanation clustering, where we were able to identify kind of different personas, essentially, of customers based on this technique, and it worked really well. And I have some questions coming in. I'm going to read the questions while Chandler, you want to talk about this one for a second?
Yeah, absolutely. And yeah, thank you all for posting questions here. We love to get your thoughts on this technique. So for sports analytics, we have a lot of fantasy sports fanatics here at DataRobot. Some of which are extremely interested in the NBA, and they did an amazing job building out a data set predicting player performance. And using the similar kind of old-fashioned technique that Rajiv and I had talked about before, which is much less easy to navigate than Andrew's, simply using Excel and row-wise explanations, we're looking at, again, which features are driving up the probability that player is going to score more points per game. And you can see across the board, cluster D is kind of green all the way down, except when it comes to things like minutes lost due to injury, right? So, these players tend to stay healthy, and they tend to play more minutes per game. And it's kind of the inverse for some of our lower scoring players. So, the interesting thing is to get to this point from where we started the data, from where we started the analysis, to sort of this level of insights, especially with the package now, would probably take about 5 to 10 minutes. So kind of the benefit of being able to quickly understand and see what's driving your data set, and also increase your sports betting winnings.
Excellent. I'm going to answer some of the questions as they come in before we get to the next example. So one thing I want to clarify, the packages here are made to work with the DataRobot product. So you have to be kind of a customer of DataRobot to fully kind of use the packages as is. Now, the approaches here are very agnostic. You could easily kind of fire up and use the same concepts and probably even cut and paste some of the code here using it outside of DataRobot, but the packages we've made have been tuned to kind of use expressly with DataRobot. One other question we had was about the clusters, and do the clusters have an order of predictive importance? Do you want to take that, Chandler? And I'm going to move to the next slide.
Yeah, and I think we kind of saw this with Andrew's example, where we can look at the average probability per cluster, and they tend to separate upon that, right? So the whole idea of doing this is that some features that tend to push the prediction probability up are going to be found together, and things that tend to push the prediction probability down are going to be found together. So there's not a forced ordering, but there is sort of an inherent ordering that can shake out from this analysis. I don't know if you have any other thoughts on that, Rajiv.
Yeah, no, I think you're right on, because what the idea of the explanation clustering is that there's going to be similar factors in your data set that lead to high predictions, similar factors that lead to low predictions, right? Because the model is going to figure this out. And so, yeah, naturally the clusters will probably represent that as well. Then we have another question here, and then we'll go ahead and go to the healthcare. How do you set the number of explanation clusters, right? So if we look at the example here, I don't know if this is the one that actually went with suicide prevention, but you can see about 10 clusters. How do you guys, and Andrew, you can chime in here as well, because I know your package incorporates this. What do we think here about setting the number of explanation clusters?
Yeah, so this is definitely going to vary on the clustering method you're going to use, but it's an example of the types of options that, at least in the ARM package, you can provide to pass into the algorithm underneath the hood and customize it that way.
Yep. And I think, there's times that, your end customers that you're giving this off to can only handle like 3 clusters. Like maybe the data naturally has kind of 8 clusters to it, but they only have 3 campaigns they're going to run. They need 3 clusters. So yes, you can kind of typically, as like with lots of clustering algorithms, kind of play around with the various settings in the density-based approaches to kind of vary the clusters. But the nice thing is you don't have to start from the beginning and say, this is the X number of clusters that is going to come out, unlike like a k-means approach.
Right. So as you alter some of those settings in terms of, say, the minimum number of points required, that's going to alter the number of clusters that are coming out.
Yeah, exactly. And I think just kind of, we settled on HDB scan because we didn't have to define the number of clusters. And so we thought that was nice, especially as we're thinking about something that's sort of repeatable. And the idea here is density, right? So as we reduce the number of dimensions with something like UMAP, we tend to increase the local density, right, of records to each other, and HDB scan is going to pick up on that. So as you play with the number of dimensions you're reducing to, like Andrew said, that's going to sort of naturally shake out into your cluster size, or the number of clusters present. At the same time, though, HDB scan, like we said before, will start to identify things as noise. So sort of a trick, and we can talk about this as sort of a best practice, is you can compare the number of points classified in a cluster versus the number of points classified as noise to use as sort of a discerning tool, along with those other metrics like AMI and ARI to evaluate kind of cluster membership. But you can adjust the number of factors to see how well your membership shakes out and where that happy medium is. So short answer, you don't necessarily have to define a size, but you can adjust the knobs to get there.
Yeah, I never thought about taking the noise like that. That's a good idea. Hey, you want to walk us through this example? I know this was someone on your team, how they used explanation clustering here.
Sure. Yeah, so this was an example of a team we were working with that was taking a look at suicide risk for active duty warfighters. And we set up a study where we were looking at matched controls. So we had a pool of folks that had suicide events and a pool of similar folks that did not have suicide events. And taking a look at that, we used the prediction explanation clustering in an iterative fashion. So we started with a predictive model, ran the prediction explanation clusters, and took a look at these clusters that came out that were sort of our first look at perhaps phrasing it as different risk groups. And what we were able to see from some of those initial results were, for example, one of those clusters had the medication feature as a really important explanation. And that triggered us to take a look back in the DataRobot platform. Let's dive into that variable, because there appears to be this cluster of people for whom that's particularly crucial in predicting suicide risk. And from that led us to create further predictive features in the next iteration of the model. So we were able to see by looking at, say, the prescriptions, there was a certain class of prescriptions that was especially helpful by looking at the word cloud output that's available in the DataRobot platform. So again, the prediction explanation clustering led us to an investigation, which led us to a new feature engineering, and ended up producing a better model on that tail end. So we can use this not just as a destination, but really a tool and an ongoing analysis to continually get further insights, refine our model, and push forward there.
Yeah, no, and so one of the things I just wanted to clarify, Andrew, so were you using text features in that model?
Absolutely, yeah. So a lot of the prescription information we might have included as, for example, a list of prescriptions as a single text feature, and picking out words and phrases from that.
Yep, so I just wanted to highlight, there was a question about using this on text features. So yes, absolutely, we can easily use this on text features because we give explanations on text features. So that's just another piece of data that we can use. So we'll keep going. The questions are coming in, and I'll keep kind of bouncing the questions off Chandler and Andrew, and kind of share a few other examples that we've used along the way. This is an example that came from some work with a bank on loan segmentation. This was an early one, I remember, that they were kind of using these explanations for, and it worked really brilliantly for them. It helped them kind of quickly kind of segment customers into 4 different groups, and they were able to kind of look at the clusters and easily kind of see what the differences were between them, and was able to kind of give their customers a really good understanding of exactly kind of how the model was doing in these different places. Let me see what else I got here. I have another, I'm going to try to mix up the questions here. What happens if the explanations don't clearly form in the reduced 2D space? Have you guys encountered this, and what would you do? Anybody want to try taking that on? Go ahead.
I'll kick it off. Yeah, I think, so what are we talking about here? So we're saying that if we flatten our explanation, so we have this matrix of explanation strength, by features in rows. If we reduce that down to, in this case, 2 dimensions from the question, what happens if the clusters don't shake out?
Yeah,
I have yet to encounter that. I think intuitively, as we kind of collapse our feature space, we're going to be creating pockets of density, and so we're going to start to see some, areas of information pull together. I think I would think that could happen if we have a less performant model. Like, for example, if there are less consistent features that are driving a probability up or down. So if you have like little signal in your data set, this is probably maybe something you want to use judiciously. I think on the flip side, yeah, I think that'd probably be the primary case that comes to mind. And I'll think about something else and kick it back to you, Rajiv.
No, and so that's an important piece, though, right? Is
yeah,
when you're using these techniques, it depends on the strength of the model. If your model is really weak, just because your problem is tough, well, the explanations are going to be bouncing all over the place, and it is going to be much harder to really kind of both get nice, crisp clusters, as well as be able to trust that, right? Because the last thing you want is to rerun the data set with a different partitioning seed and getting totally different clusters and totally different results. But I think, yeah, anytime you're working with stuff with low signal, that's it. If you have a fairly good model, in my experience, most of the time you get pretty good clusters because your model's been able to find those different areas, those different kind of groups in there. Okay.
Yeah. And I would think, and I would also say too that I wouldn't always stop at 2 dimensions. I would try to iterate between 2 and higher, and sometimes you may be collapsing too much down to 2D for certain data sets, particularly ones that begin as extremely wide up front. So that's, you can't visualize that, but again, I would test that one out. Okay.
Yeah, I mean, and now with the SHAP, when we can kind of get it as wide, it'll be curious to kind of take a really wide data, somebody's building a model with, let's say 300 features, and we want to kind of try to do that and see how well, how the approaches work on something like that, and the range of explanations as well. Here's another example. It's pretty self-evident. They use the explanation clustering, and we're able to kind of identify some key characteristics for agents that had the highest 15% of predictions. So just think of yourself, right? You've built this model to identify, like, hey, these are the likely, agents that are likely to sell. But now you can just take that information, kind of put it into 3 different types of groups to help explain it back to the business. And then they can actually work with these groups and say, hey, maybe these promising stars, if you can identify these, we're going to treat these people as differently. Okay, let's see. I'm going to try to see if there's another fun example here that I want to use. Oh, here's a question. Can you please describe the steps for time series data? Am I going to have to answer my own question here? Have you done any explanations with the time series?
Personally, I have not. So I'll have to defer back to you on this one. Yeah.
So the example here that I'm showing actually was one where it was kind of a bit of a time series where you can see the differences between kind of day 1, day 2, like that. The steps really aren't really any different for time series because with DataRobot, for kind of any prediction you get, if it's a time series and I'm predicting 7 days ahead and it's a multi-series project and I have jewelry and lawn care and what are the other departments in a store? I don't know. Bath. I can, for any of those different series, for any of the forecast distances with DataRobot, get the predictions. So it's just a matter of taking those predictions out and then applying the same types of clustering. And a little bit of that then is starting to decide how you want to group the data. So for example, will you do your explanation clustering probably by series? So you're not going to mix what's happening with jewelry with what's happening with lawn and garden, for example. But the methodology is still kind of the same approach that you would use. Here's another example. This is one from Scott Lundberg. If you want to kind of go out and see this in an academic paper, Scott's kind of published this a couple years ago where he's just used kind of a hierarchical clustering to be able to take those explanations. And then you can see here how he was able to kind of identify kind of various groups using the classic adult data set as well. Okay, how are we doing on time here? Oh, we are almost out of time. Let me see if there's a final question here. Do we have any samples using nodes and edges? I don't even know how to answer that. Well, anything else you guys want to add, Andrew, Chandler?
Yeah, Andrew, you want to kick it off? Or?
Yeah, just wanted to reiterate here, these packages that we've put together here are a first stab at kind of getting these techniques into a solidified form. Definitely improvements to be made. So we encourage you to try them out, kick the tires, and get back to us on what's working, what's not working, and where you think it might get better. The purpose of releasing these to the DataRobot community is really to get it in the hands of folks like yourselves and take advantage of your experiences, your insights that you're getting from the problems you're working with. So let's pull together as a community and see what we can push this forward and make it even better.
All right. Well, hey,
yeah, thanks,
I
Andrew.
just want to. Oh, go ahead, Chandler.
Go ahead.
Oh, I was just going to thank everybody and kind of sign off. So.
Go for it. Yep.
Okay. Well, thanks everybody for joining. Hey, feel free to reach out if you have any questions on community. So at community.datarobot, we have a nice discussion group where you can talk about these things, grab the code from GitHub. If you have, if you're a customer and you have a CFDS, let them know if you're interested. They can give a more detailed presentation as well. And then look for more of these. We have some more learning sessions coming up. I don't know, Jack, if you know the next one. I think next week we're going to be talking about using DataRobot scoring code for those of you that want to build models with DataRobot, but then take that code outside of DataRobot and use it. We're going to be talking about that. And then we have a lot more good modeling stuff coming up in the next couple of weeks as well. The last thing I want to mention is the AI experience. So if you're new to DataRobot or a current customer, go to our DataRobot homepage. We have a big conference in 2 weeks. I'm setting up a lot of the sessions. They're going to be around lots of great data science topics. So it's another opportunity to kind of learn a bit about data science as well as DataRobot. Thanks, Jack.
Thanks, guys. Again, as Raj mentioned, any future opportunities for learning sessions, you could go straight to the community page. And again, if you have any questions that are related to this particular learning session, you could email us at aisuccess-webinars@datarobot.com. Thanks again, everybody, and I hope you enjoy your weekend.
Thanks.
Thanks, everyone.